Take a look at the computer or phone you're using right now. Every physical object around you, including your own body, has the theoretical potential to become a black hole. It all comes down to a single mathematical boundary, known as the Schwarzschild radius, or the gravitational radius. This rule dictates if you take an object's entire mass and crush it into a specific microscopic sphere, its gravitational pull spikes dramatically. Cross that exact threshold of compression, and gravity becomes so intense its escape speed equals the speed of light. You don't need to worry about collapsing into a dark void today. For an average human, that required sphere is impossibly tiny, and there is no natural mechanism on Earth capable of generating that level of pressure. To actually witness this mathematical threshold being breached, we have to look out into the deep universe for an environment with enough natural gravity to crush matter past the breaking point of physics. Out in deep space, massive stars exist in a delicate equilibrium, holding their massive shape through the continuous nuclear reactions burning inside their core. But as a massive star reaches the end of its life, that internal core starts running out of fuel, causing its outward push to fade. Without that internal pressure, the star can no longer hold itself up. The core violently collapses inward under the crushing weight of its own outer layers. That immense cosmic weight does exactly what we couldn't do on Earth. It successfully compresses the core's mass directly past its Schwarzschild radius. The complete structural failure of a dying star provides the exact amount of force required to shatter standard physics. This entire collapse into a mini black hole doesn't take millions of years. It happens in mere milliseconds. With its gravity now running wild, the new black hole instantly begins consuming whatever is left of the dying star around it. This sequence happens so quickly that the outer layers of the star don't even have time to react before the entire structure detonates. This chart compares stellar energy output. The first bar shows the total amount of energy our sun will produce over its entire billions of years long lifetime. The second bar shows the supernova explosion, releasing an amount of energy in a single moment that completely dwarfs our sun's total output. What remains at the center of that blast is a permanent gravitational pull so massive that nothing, not even light, can ever escape its perimeter again. This terminal collapse triggers the rapid, violent birth of an inescapable cosmic trap. In the empty space immediately surrounding a fully formed black hole, the standard rules of reality begin to fail. Because of the extreme gravity, time itself behaves entirely differently near and inside the boundary of a black hole compared to the rest of the universe. Curious, which raises a question. What happens when two of these inescapable gravitational heavyweights drift into each other's paths and collide? This diagram illustrates the two possible outcomes of that clash. Following path A, the gravity wells might fully merge to form one massive, deeper entity. Or, following path B, they might fight it out, violently flinging one of the black holes away into deep space. Fortunately, you don't need to worry about getting caught in one of these clashes. The closest known black hole to Earth is a safe 1,600 light-years away. While those massive, time-bending anomalies stay safely at a distance, the exact mathematical rule that birthed them is sitting right in front of you, hiding quietly inside your computer.